OK, so the last piece of the puzzle for this case study is to evaluate it. We've shown visualizations, looked at the source code. Now let's talk about the pros and cons of what we've done. And as usual, there's almost always good things and bad things with any technique. And so we have to be fair and balanced and make sure we show the good with the bad, or the bad with the good. So let's start off by talking about some of the good things about this solution. Probably the most obvious one, and this is always true with parallel streams, is there's very little programming effort, syntactically at least, to convert between a sequential and a parallel stream. So it's often minuscule. So here, again, is what we see with the sequential version of this stuff. That's what it looks like. We get the input, the works of Shakespeare, turn it into a sequential stream, map that to process input, and collect it to a list. OK, so far, so good. Here's the only difference for the parallel version. You can see it's exactly the same, except we have parallel stream here instead of stream. Oops. So you can see here we have parallel stream instead of stream. And that is the only change. So boom, very, very simple. That's often all you need to do. Now, again, depending on various factors like what kind of data sources do you have and what operations you're using and what kind of hardware you've got and so on, it might be a win or it might not be a win. But we'll just pretend for the moment that it is a win. And clearly, in this case, it's a win. And how do we know it's a win? Because we benchmarked the results, and we can see that there's a big speed up going from sequential streams to parallel streams. And even though sequential streams were a little bit slower than not using streams at all, there's some abstraction penalty. The ability to get massive speed-ups with minuscule work is a nice thing. And what I should also mention, because I've done these tests every time, you'll get different results with different hardware platforms. So this particular one was running on a quad-core Lenovo with 32 gigabytes of RAM. And I have maybe an 8-core Lenovo with 64 gigabytes of RAM or 128 gigabytes of RAM or something like that. And the performance is slightly different, but usually you get a better speed up. What's interesting, by the way, is the hardware of a given core typically hasn't gotten much faster. In some cases, it's gotten slower, but you got a lot more cores. So you get a real win from parallelization on those platforms, even though the cores are about the same speed as they were in the previous generation, but you've got more of them, so you get a better speed up. This is the same thing using a MacBook Pro, which had less memory, but faster processors. You can see it was 2.7 versus 2.9. And so as a result, it takes less time to do the processing, because each core is faster. And then you can also see that there's a little difference in which ones win. And that, again, very platform dependent. Now, on Intel processors, they have what are called hyper-threading, which means that a given physical core actually is, quote, hyper-threaded. And I'll talk about what that means in a second. And interestingly enough, on the Apple, at least the MacBook that I've got here that is using the Apple M1 chip, it is not hyper-threaded. The previous version was an Intel processor, which was hyper-threaded. The new ones are not. And we could debate ad nauseum which one's better. Honestly, I'm very impressed with the MacBook, especially in terms of its power utilization. My quad-core Lenovo is an incredible power hog. And if I don't keep it plugged in, like if I'm flying on an airplane, I get about 2 hours of battery life on that darn thing before it just goes away. With my MacBook, which is actually much faster and way more cores, it'll last like all day. So it's really interesting power management. I think that's one of the big wins you get with the Apple chips. So what is a hyper-threaded core? Basically, it supports what's called superscalar architectures, where you can execute more than one instruction during a clock cycle by essentially pipelining the instructions. And you can read more about superscalar processing. So you can actually have a bunch of stuff going on in parallel and steady state. The tricky part here is that not every program lends itself to superscalar execution without an enormous amount of work on your part and or the part of the compiler or assembly writer, the person writing the compiler or the assembler. And so that's why the hyper-threading is not as good as having a hyper-threaded core is not as good as having another physical core, where there really truly is more processing able to go per unit time. But you can see some improvements by using hyper-threading under the right circumstances. that was a little bit of a side note. Now let's talk about the cons with the Search with Parallel Streams class. As I always like to say, not everything is unicorns and rainbows with all this stuff. So just because there were little tiny minuscule changes needed to go from sequential to parallel doesn't necessarily mean that you're going to end up with the best solution. So here's some stuff that we will talk a bit about later. At least for this particular hardware and this particular version of the Java virtual machine and so on, there were a couple other implementations that ran faster than the parallel streams one. In particular, the ones that use completable futures were faster, and we'll talk about completable futures later. As a general rule of thumb, completable futures are typically faster than parallel streams because the abstractions of the programming model lend themselves more readily to the underlying processing elements that we have in a multi-core processor, but they're a little bit harder to program. So the great thing about streams is it's pretty easy to program once you have the paradigm for sequential streams, and converting from sequential to parallel streams is like a snap of the fingers by Thanos. You just, boom, you're running in parallel. So it typically gets you good performance, but maybe not the best performance. And something else that's worth noting here, you'll see that there's a thing up here that says parallel split iterator. That's yet another variant of this which does parallel processing in 3 dimensions, and we'll talk more about that. So it'll do it in terms of the input strings. Each work of Shakespeare runs in parallel. Each phrase runs in parallel. And then searching for a phrase within a work of Shakespeare also runs in parallel. So we get this little trifecta effect there that's pretty cool. So, of course, your mileage may vary, as they always say for miles per gallon on cars, depending on what you're doing. So there's no substitute for benchmarking and experimentation. You need to benchmark your stuff to see, is this a win? Is this not a win? I don't know. Benchmark it. And we'll talk, if we have time, we'll talk about the parallel split iterator version of all this stuff, which for this particular environment was the fastest, although it's not, it's not wildly faster than the parallel streams version, both of which are wildly faster than the sequential streams version. And when you see the parallel split iterator version, you may ask yourself, was it really worth all that extra work? Because it turned out to be a lot of work to make it be a parallel split iterator version. And the thing that's cool about that, as I mentioned before, is it's very aggressive, and it's got 3 dimensions of parallelization taking place there. So you can do better, but it may be harder to program. And with everything in life, you have to figure out, is the trade-off worth it? If you're building some kind of game engine, maybe so. If you're just building something that's fairly straightforward, maybe you're happy with the speed up you get from using parallel streams out of the box in the simple way with minuscule changes. So that's the end of the overview or the evaluation of the Java Search with Parallel Streams case study. At this point, hopefully you have everything you need to go forth and do well on programming assignment 1B.